do with models and why we're using models and the various ways that we can use different types of models. So first of all, let's look at like why even use models versus just thinking about what actually really happens in real life. So one important reason to use them is you can visualize things in 3D that you can't normally see, right? So we can't actually see any unique own individual compounds, but we can use different types of models to actually visualize that and visualize it in 3D. You can use them to understand conformations, energy barriers, and so one example of this would be looking at Newman projections. So kind of a review here. You guys probably have already done this in lecture. We'll look at Newman projections. Some of our assignment this week will be looking at Newman projections. So if we've got a Newman projection like this of butane, which projection is that? What do you call that? Anti, or like it's also a form of a staggered conformation, right? Is this an energy minimum or an energy maximum? It's an energy minimum. So then this guy here, we're still looking at butane, okay? What would that one be? Energy minimum or maximum? Max. And that's our real absolute max, right? So what is this? This is your eclipsed. And then this guy here, what is this one? This is gauche, right? Is it a minimum or a maximum? It's a minimum, right? It's not the minimum. The biggest minimum would be down here, but it is if you look at the energy of butane in the conformations, it is one of the lower points, okay? So the third reason to use models is they can be used for predictions too. Now, in lab, we're going to be looking at computer models. Eventually, in workshop, though, you're going to be using physical models. So we're going to look at both of those right now, comparing physical models versus computer models. So one of the strengths of physical models is that you can actually see them and handle them, okay? So they are tangible. You can usually with physical models, easily see things in 3D because it's actually something you hold in your hand. And if you get really expensive models, they are also made to scale. So for example, you could buy a model of a specific compound or a specific protein or specific binding site, and that would be made to scale for that particular situation, okay? Now, a disadvantage is kind of the opposite of that, though. In general, without purchasing the expensive one type of model kind of thing, if you're looking at general physical models, the bonds, the angles, and the lengths are not to scale. They're generalized. And they're not molecule specific usually. So like the models you'll use in workshop, which are the same models that they've mentioned that you could check out or possibly purchase, are not to scale because they're generalized models for organic chemistry, okay? For the computer models, as far as the strength, they are infinitely variable, right? Because you can use the computer to vary all sorts of parts of the molecule and tell the computer to do all sorts of different things, whether they are, if it's, you know, whether it's actually something that'll actually happen or not, you can still put in all these variables. They can calculate bond angles and bond lengths. And it just depends on how good the program is, how well defined the program is as to bond angles and bond length, how good these calculations are, but it can make those calculations. You can optimize a molecule for a specific geometry. So we'll do some of that this week. You can also use these for predictions. And we'll use some of that this week, predicting what would happen if we change different variables on the molecules we're looking at. Biggest disadvantage is that they are, for the most part, still only 2D. And you can't actually hold it physically in your hand with a computer. You can use, 3D technology and use a 3D screen and so forth, but it's still not something that you can physically hold in your hand. So they're not tangible with the physical models, all right? So there's a couple things that we want you to be aware of and make sure that you are able to complete this week for this week's experiment. So a couple things you may want to even practice before you come to lab this week. First of all, remind yourself about electron density maps and what is involved in reading those. We're going to take a look at different electron density maps and what's involved. So this is in chapter 2 of McMurray. Just a reminder, if you have a red section of one of these maps, what does that represent? High electron density, right? And the blue to purple sections are then low electron density, right? And then we've got the blurring of the colors in between. So we'll take a look at this and make some predictions based on electron density maps. Another thing to be familiar with is what is called the Sawhorse Representation. So we've looked at Newman projections, now we'll look at Sawhorse representations. So this is a way of looking at a molecule with just basically looking at its backbone, okay? So if we have something like this for ethane, it's a way to look down a bond, but it's a different perspective than looking at a Newman projection, okay? So if we drew this in terms of what atoms were involved without actually showing the atoms, we draw something like this. And that would be the Sawhorse representation, okay? So you can draw it, that is staggered, we could also draw it eclipsed. We can look at it both directions, okay? Another thing to be familiar with is using wedges and dashes. So the wedges are what's coming out of the paper or out of the board. The dash is what's going into the paper or the board. And what is just the straight line, remember, is in the plane of the paper or the board. Okay? So we'll use some of that this week. And then also, I know you guys are practicing with your chair conformations, and we're going to draw a lot of those. So you want to make sure you have practiced with those guys. So you want to make sure you can draw the actual conformations. This straight here. And remember, it's a series. You want to think of it as a series of parallel lines. So we've got these two are parallel, these two are parallel with each other. And when we put substituents on there, what are the two positions that we talk about? Axial. So we've got axial up and equatorial out, right? So you want to make sure that you're familiar with, and sometimes depending on how this, you can look at it this way, how do you put those axial and equatorial substituents on? And make sure it's clear what it is, too. So when you draw it, make sure you're showing it clearly as axial or equatorial. All right. We'll also look at then flipping the chair, so then drawing it the other direction, okay? So remember, flip our chair here. So we'll have to draw it then the opposite, right? So now we'll start with our start here of our parallel lines going this way. Okay, and so then our substituents are going this way. So when you do the chair flip, the position of the substituents is changing between axial and equatorial. So we'll look at that, okay? Questions with any of that yet? Alrighty. So for lab this week, there's some things you're going to need to bring with you. It'll be a little bit different than usual weeks. So you will still need, still plan on, you're going to need your lab manual. You're going to need your notebook because you'll be collecting data for your melting point information. And you'll need a pen to write in your notebook. But you also should bring pencils and erasers, or pencils and an eraser. Because a lot of times we're going to check things and then have you change things a little bit. So it's a lot better to do the worksheets with a pencil than with a pen. If you have a model kit, you can bring that with you. As far as the pre-lab is concerned, you're not going to put anything into your notebook, but you should look at Chapter 2 in McMurray. So you want to look at figure 2.3, and then sections 2.3 and 2.4, and bring your McMurray with you because there's some questions in the experiment that pertain to what's in your actual textbook. And then you also want to review chapters 3 and 4. Okay, so instead of writing your pre-lab in your notebook, that's what you're going to do. You're going to, in 3 and 4, you're looking at structures and stereochemistry of alkanes and cycloalkanes. The other thing to bring with you, if you have it, is a laptop. So if you can bring your laptop with you, you can use WebMO on your laptop, which is what the program we're going to be using. Okay. So I highly recommend, especially the double sections. So Tuesday morning, it'd be a really good idea to bring your laptop if you have it, because we're going to have to split that computer lab between the two sections, and there's only 15 computers in there. Okay. So if you have your laptop, bring it to lab this week. It doesn't matter if it's Mac or PC. We've had everything work on both. As far as programming or anything like that, you just need a web browser. Firefox and Chrome tend to work the best with WebMO. So if you've got laptop with that on it, it'd be really helpful if you bring it this week. All right. Let me show you now. I'm going to show you how to do a couple things with WebMO, and then we're going to talk about some other reminders and such for melting points and that sort of thing. It's slowly coming to life here. So the website is in your lab manual. It's kind of an old picture of it, basically. But you want to go to curry.chem.hope.edu, okay? And once you do that, you will get to this page, and then you will click on WebMO, okay? Now I'm going to have a volunteer come help me here. you'll make sure you click into organic chemistry as well, okay? Not general chemistry or any of the other options. We want organic chemistry. And then when you go to sign in, you're going to use your username for your email without the @hope.edu. And you'll use your password for your email. You can watch this now. And then what you'll have to do is after that, you need to select, I'm just going to show you that. There's no group password, but what you've got to do is select what lab section you're in, and you want to pick the right one. You're only given this option the first time you sign in, so you want to make sure you know what lab section you're in the first time you sign in so that you get into the right lab section. So 6. Yeah, so it's 25506. And then once we hit login, then yeah, hit login. Then you're in, and the next time you go to sign in, you won't have to put in the lab section, okay? All right, I'm going to log you out, so you don't have to have all my demo. You're all set. Thank you. So here, let me get myself in here real quick. Because you have, like that first time you have to put your lab section in there, I had to use volunteer because I've used, obviously, you can tell by the number of jobs in there, I've used WebML quite a few times, okay? So you wouldn't be able to see me selecting any lab sections. So when you get in here, what you want to do first of all is click on New Job. We're going to create a new job. So I'm going to show you a couple features with WebML and how to do a couple of calculations, and also how to prepare some of your assignment, okay? So I'm going to start with my example being propane. So in order to build something, you want this build icon to be selected. It usually, when you go into a new job, is like the default of what is selected, okay? And its default is to have carbon atoms ready to be joined together, but if you want to change it, you go down to this periodic table and then you can change it to a different type of atom, okay? So I'm going to start with propane. So I'm just going to left mouse click, I get one carbon, then I'm left mouse clicking and dragging at the same time to get the second one bonded, and then left mouse clicking and dragging to get the third one bonded, okay? So it doesn't have to be perfect the first time you draw it. We're going to, your instructions will always tell you to use this comprehensive cleanup. So we'll clean it up by clicking on this wrench, then it'll make it more symmetrical and make it so that things are more in the place they're supposed to be, okay, more lined up the way they're supposed to be. You can use this arrow here. You click on it and then left mouse click to rotate your molecule around so you can look at different aspects of it. There's going to be times that you're going to need to calculate things like bond angles and bond lengths. The way you do that is you click on adjust, which doesn't seem like it, like the sound of the icon doesn't sound like what you think you should have to do, but that arrow there is what you want. And then you'll select the atoms involved in whatever you're looking at. So if we wanted to know the bond length between this proton and this carbon, we would just click on those two atoms, and then down here at the bottom, it tells us the bond length, okay? Or if we wanted the bond angle between this proton, this carbon, and this carbon, then that would give us the bond angle down there, okay? Another thing that you will be asked to look at is the dihedral angle. So it's this angle in between of, you basically have 4 atoms involved in a dihedral angle. So if I click on this proton here, now we've got those 4 atoms, and we have the dihedral angle of what's going on between here, here, and here, okay? And so again, it's listed down there in the bottom. Now when you rotate, you'll lose those things, but you can go back to the adjust arrow and then start selecting or unselecting to get whatever calculation you want. So to unselect, you just click back on the things that were selected, and then those disappear. Okay. When you are asked, besides using the wrench, to go in and do different calculations on your different molecules, you're going to click down here on the bottom, the lower right, this continue arrow, okay? And it's usually going to ask you, it's not nearly symmetric, do you want to still continue without symmetrization? Yes, we will do that because we're going to take care of it in the calculation we're going to do, okay? So this first one is going to be like one of the first calculations that you have to do with ethane. We're going to use the Tinker engine and then click OK. And then what we want is we're going to look at molecular geometry, or geometry optimization is what we're looking at. Okay. In the job name, it will automatically just give you the molecular formula of whatever you're looking at as your job name. What you probably want to do is call that something unique. So we could give it just the name of what it is, or you could put dash, like your initials, on it. It's helpful if you actually put something identifying on it for us to know whose it is, because we can go in and look at our lab section and look at all the calculations that were run for everybody all at once, but they're all listed by this job name. So if you give me, propane dash, your initials or something like that, then I'll know who built that one, all right? So then you're going to select what calculation you want, what force field, this is all correct, and then we'll click the arrow and it'll start doing the calculation. For the pretty simple calculations, it will be done pretty quickly, so you can just click refresh and then it's done within a couple of seconds. One of the series of calculations you're going to look at is you're going to look at butane, and you're going to look at all the different conformations of butane and then make calculations based on those conformations. That one takes a little bit more time. It probably takes like 10-15 seconds depending on how many of you are trying to do that calculation all at once, okay? So that one, it may take a couple times refreshing it to get that one to pop up. But once it's says that it's complete, you can just highlight it. And so it still looks like our propane, but now we want to go down and get information about it. So in this case, we were figuring out the total potential energy. Here's the potential energy that it calculated for propane. So like when you go to do the calculations for ethane, it's going to ask you to look at the potential energy. Go down to the box to look at that, okay? So at some point, you'll also look at the electrostatic potential map of compounds. I'm going to show you how to do that as well. Go back to the job manager, and we'll get a new job here. The example I'm going to use is looking at chloromethane. Okay, so I'm going to start with our carbon here, but I've got to go over to the periodic table and now select chlorine, and then left mouse click and hold it to attach the chlorine to the carbon here, okay? Now I'm going to click on the wrench because that does that first order optimization, okay? So it adds the protons on for us, and then we've got our chlorine on our carbon here, so we've got chloromethane. We want to go and run the calculations that we need for creating the electrostatic potential map. So again, we're going to have to use the arrows here, okay? And then say OK again. This time we're going to use MOPAC as our engine for these calculations. Click the arrow. And then we want to select what type of calculation we're doing. We're going to look at our molecular orbital calculation, okay? And so then it tells you to use theory of PM3, and all of this is going to stay the same. So a lot of times, once you make the selection of the calculation, you don't really have to change anything else. But double check what your lab manual says. Also, make sure there's a lot of instructions in your lab manual. Make sure you are following them step by step, because if you miss a step, it's not going to work, okay? So here's our chloromethane. And now we're going to scroll down. And we have more tables than we had before because of the type of calculations we did. Click on electrostatic potential here in the magnifying glass. And so then it gives us the electrostatic potential map. And if you just left mouse click on the map, scroll this up a little bit, then you can look at the compound and how the different colors line up, okay? And so you're going to be looking at what you construct and see how the different colors line up to help you figure out where electron density is, okay? So make sure you rotate it around and look at all sides of it too, and not just the side of it. If you click on this icon here, which says preferences, you can change, so you can change the atom size. You can also change how transparent or not it is what you're looking at, okay? So now I've made it more transparent so that you can look at it a little bit better and see the actual atom through it. So if the initial settings make it hard for you to see the molecule through it, you can change those to make it a little bit easier, okay? Now for the last part of the experiment, you're going to be looking at building morphine, which is a pretty complex structure. So the structure is given in your textbook, and we have physical models of morphine to help you as far as building it. Once you build it and run different calculations on it, you're going to want to print it so that we can see what it looks like and make sure that you've drawn or built the right structure, okay? So when you do that, it's not going to be an electrostatic potential map, but I'm going to use this as kind of an example. You want to line up your molecule as best you can in the screen so that you can see all of the areas of it. And then what you're going to do is use Alt Print Screen, or with the Macs, you're going to use basically the screenshot. And we want to take a screenshot and then open up Word and paste that screenshot. So you can use Control-V or you can use File, Paste. We'll put that screenshot into the Word document, and you're going to be printing this last page to hand it in. And you could also put the calculations on this last page as well, type those on there. But make sure you don't forget to print this page, because there's not a page in the worksheets for it except for giving the energy calculation. So make sure you don't forget to print this, because this is part of the assignment. All right. Then once you've worked through all the parts of the worksheets and printed this, then you're just going to hand in that whole packet to us next week. Okay. All right. Questions any of you have on this before I talk about melting points? Good? Okay. Just remember, follow the instructions carefully in your lab manual, because it's easy to skip over things and then things don't really out quite right. But if you are having trouble, make sure you check with your laptop. They will help you out. Okay? All this is shutting down. Out of here. And in the end, you go to the job manager and you can log out when you're all done. All right? Okay. A couple things to keep in mind for melting points and other things. Other items that have come up in lab. Make sure that you're collecting melting point ranges. So not just a number, but it should be that range of where it starts and ends melting. Okay, so make sure you actually report a range. And that is for your fast melting point ranges as well as your slow melting point ranges and your mixed melting point range. All of those, make sure you're always reporting a range and not just one number, all right? When you are collecting the melting point ranges, just be careful with your two solids. Make sure they're labeled. Make sure they get back in your drawer again. Make sure that they're in something. I don't recommend storing them in weigh boats because they want to tip over really well, so make sure they're in something that's not going to tip over. But when you're done using the melt temps, make sure you get, or collecting masses, make sure you get them, put it back in your drawer, and don't leave them out, because once they're left out, especially if you can't identify them very well, they're just going to be tossed whether you're done collecting the data or not. So be really careful with that, okay? You're collecting melting point ranges, but also don't forget that you need the masses of your solids as well, because you need to calculate your percent recovery. So in lab this week, you want the melting point ranges, but also don't forget to get the dry masses of what you recrystallized last week. Before you leave, also don't forget about your area in the hood, cleaning things up, capping waste, wiping things down. Wipe up your area, make sure all the chemicals and everything are cleaned up. Dry them if like you have a condenser leaking, things like that. And then also the melt temp areas, just make sure if you spill any solids, sweep it up. The balances, sweep them up. Keep everything as neat and tidy as possible, all right? Also cap your waste before you leave, and make sure you pull your hood sash down, turn your lights off, things like that. With the waste, we had a couple incidences of water in the organic waste last week, so remember, no water in the organic waste, okay? So when that happens, layers form and we have to separate things out. So don't forget, no water in the organic waste. Also for open lab, just make sure that when you're coming to the open lab, it's not when you're missing a class, you don't want to make a workshop, things like that, to come to open lab. You need to do it at a time when you have a break in your schedule, okay? So don't come if you have class at that time or you're missing workshop to be in open lab. You need to attend those classes. Let's see, other things here. Oh, just a reminder too, for those of you with the morning labs, the PHLEPS opens at 7 a.m. It's cold, it's not the full spread, but there is breakfast for you to eat before you come to lab each week, so make sure that you eat before you come to lab. Both 7:30 labs and 1 o'clock labs, make sure you've eaten before you come to lab, because 5 hours is a long time to be on your feet and so forth without eating, all right? Questions you guys have? Yes?
So for that picture we have the printout for like this week's class.
What are you drawing in comparison to?
No, it can be like
What are you up to? Sanford?
it's not.
It's
It's just going to be
you're doing this.
How do your axes compare to like 60-ish? No, it's more than 90.